Alright, so we're going to work on 11.2. It's evaluating limits analytically. I kind of renamed the section to analyzing limits, or evaluating limits analytically. Analytically just means with numbers rather than relying on a graph. So by hand, using numbers, solving the problems that we might run into with just the function itself, just that equation. So first we're going to look at one-sided limits, which is it's kind of a way to look at limits that wouldn't exist otherwise by our previous definition of limits. And so it gives us another way to also define limits. And you'll see where we get there. There's something called the dividing out method for finding limits that give us trouble. The rationalizing method for limits that give us trouble. And there's this thing called the difference quotient that becomes very useful in calculus. So right now we're just going to go over some of the concepts of all the stuff that's involved. So just the concept of a one-sided limit, and maybe a quick example. So in the previous section, when we talked about limits and we defined it, the limit was defined as, grab another color, let's say that there's this point C. So the limit, and this would be then f of x, this graph is f of x, the limit as x approaches c of f of x, it was defined, if we look at c, let's draw a line up there so we can see what's going on. When we look at the right, as we keep putting in x values that are to the right of c but very close to c, and x values into this function that are close to c but on the left of c, the limit was this number that both sides were approaching. And we called that, and when we say the value of the function, we mean the y value, and we called that L. So if on both sides we were approaching the same number, then we called that the limit. We said the limit existed. Okay. Well, sometimes we'll have a function like a root function, a square root function, and it'll start like this. It'll just start right here, and then it won't exist over here. So it's only in the first quadrant here. The square root of x, this could be. It's believable. Well, what would be the limit as x approaches 0 of the square root of x? On the right side, as we put in values that are close to 0, like 0.01 and 0.0001 and 0.00001, we're going to get numbers that are close to 0, but on the left, this graph doesn't exist. This function does not exist for values that are less than 1. So we can't do anything over here. This function doesn't exist. So by the original definition of the limit, we cannot approach from the right and the left. So what do we do about that? Well, we basically say, who cares about the left? Let's not go with the quote limit. We'll kind of modify it a little bit. We can do values from the right, so those will be the only ones that we'll care about. So we'll look at limits from the right, and that's how we say that. We put a little plus mark above there, like where you would put an exponent. We put the superscript plus, and that means from the right. So from the right, the limit as x approaches 0 from the right would be 0. As we put in numbers into x that are really close to 0, square root of 0.01, square root of 0.001, and so on, that's getting really, really close to 0. So the limit as x approaches 0 from the right of square root of x is 0. It gets closer and closer to 0. We could also have another function, just kind of make one up, that comes over here and there's nothing at this point and it only exists on the left. Well, for this function, f of x, we could say, let's look at the limit as x approaches, we'll call this c, as x approaches c from the left. Okay, so from the left would be a negative mark, and from the right would be a positive mark. All right. So now we can talk about functions' limits just on one side or the other. So if we had some function like this, we could define the limit differently now. It's pretty much the same, but it's a little bit different. So if this is our point C, and this graph is f of x, or this is the graph of f of x, then if we look at the right-handed limit, that's what we call it, the right-handed limit, the limit as x approaches C from the right of f of x, let's see that number, let's call it L. It's approaching L. And the limit as x approaches C from the left, so we can look at what's happening from the left, well, it's also approaching L. Okay, so the limit from the left, or the left-handed limit, is equal to the right-handed limit. So just the limit, as we defined it in the previous section, a regular old limit that has to have the same value on the right and on the left. Since the right-handed limit and the left-handed limit, which is just another way of saying the values that we're approaching when we're on the right of x and on the left of x, since they're the same, then our limit is L. It's just another way of expressing what we had in the last section. Right? And sometimes if we pick our function just weirdly enough, we'll get functions that have right-handed limits and left-handed limits, but the right and left-handed limits are not the same. So if we said f of x f of x equals the square, or the absolute value of x over x, then what's going to happen as x is positive? It's just basically x over x. So x, if x is 2, then we divide x by x. 2 divided by 2, that's just 1. So when x is 2, then y is 1, and if x is 3, then 3 divided by 3 is 1, and you can see it's just going to be this horizontal line. Well, where does this start to break down? Well, we certainly can't do 0. 0 divided by 0, nothing can be divided by 0. So let's come along here. We know at least at 0, let's just say there's no graph there. We'll put a hole right there. Now as we go negative, now let's say the f of negative 1, that's the absolute value of negative 1 over negative 1. Absolute value of negative 1 is 1. So 1 divided by negative 1 is negative 1. So now we jump right down here. It's not defined at 0 again. We're at negative 1. And f of negative 2, that's negative 2 over negative 2, but it's the absolute value of negative 2 over negative 2. So the absolute value of negative 2 is 2. 2 divided by negative 2 is negative 1. So you can see we're going to keep getting negative 1. So here's an example where what's the limit as x approaches 0 from the right of absolute value of x over x? Well, that is equal to 1. From the right, we're always at positive 1. But the limit as x approaches 0 from the left of the absolute value of x over x. From the left, we just looked at it and we are approaching negative 1. So this right-handed limit and this left-handed limit do not equal each other. So the limit as x approaches 0, which is, we're not saying right hand or left hand, we're saying just the limit, it doesn't exist. So you could say does not exist. So that's right and left-handed limits, one-sided limits. And if we want to analyze one-sided limits, which we will in the next video, we just need to think about what's happening on the right or what's happening on the left, as indicated by the problem. Okay, so now we'll look at the dividing out method, which we'll use a Nice simple little example here. What if we had some function f of x is equal to x squared? Actually, before we do that, in the previous section we had nice functions, which would like f of x equals 2x squared plus 5x minus 3. And we might say, what's the limit of this function as x approaches 2? What's the limit as x approaches 2 of 2x squared plus 5x minus 3? Well, what we're going to want to do more and more is just to be able to plug the number into the function. Those are the limits we're going to be more interested in. We're going to actually become less interested in right-handed and left-handed limits, and just want to be able to create a function that we can plug the number into. And this one works great. You put 2 in there, you get 2 times 2 squared plus 5 times 2 minus 3. That's going to be 4 times 2, that's 8. 8 plus 10, that's 18, minus 3, that's 15. And this is a parabola. It's a polynomial. It's nice and continuous. There's no breakups. It's not piecewise. It doesn't do anything weird. So we can just plug this number in, and of course, on the right and on the left, it would also approach 15 if this function is 15 at 2. That's great. Those are nice functions, but what happens if we have a function more like this one? Function is this rational function, x squared plus x minus 6 over x plus 3. Now what happens when we want to look at the limit as x approaches negative 3 of this function? We don't have to do a whole lot of work before we find out. When we put negative 3 in here, it's fine in the numerator, we'll get some number. When we put it down here, I think in fact we'll get 0 up here. And you can get 0 in the numerator, but when we put negative 3 here, negative 3 plus 3 is 0. You cannot have 0 in the denominator. Something divided by 0 is a big no-no. You can't do that. It's undefined. There's no definition for dividing by 0. So what can we do about this? Well, put simply, this limit is the same as this limit, of course. It's going to be same as this limit because they're the exact same thing. It'd be the same as if I factored this this polynomial, which would be x plus 3 and x minus 2. Okay, remember from our rational functions section, these two being the same, that means there's a hole at negative 3, which means that our... Okay. So this function looks just fine. It looks all continuous and normal, nothing weird, no vertical asymptotes or anything. But we have a hole when we get to negative 3, because all along these were canceling each other out, always canceling each other out, until we get to negative 3, and the only issue there is that we're dividing by 0. So the cool thing about limits, though, like this function technically, really technically, is not equal to just cross these out and you get x minus 2. It's not equal because when you plug negative 3 into this function, nothing bad happens. But when you plug negative 3 into this function, you divide by 0. So they're not the same, but their limits are the same. So we could just keep on going and say that this limit is equal to the limit as x approaches negative 3 of if we just canceled these out and left x minus 2. Now let's see what happens when we plug negative 3 in there, try to see what the limit of this would be, which is direct substitution. That would be negative 5. So how wonderful that we can do that. If we can cancel some stuff out, hopefully cancel out the factor that's causing all the commotion, then we can be left with something that we can plug into. Okay, so that's the dividing out method, and we're going to try one more kind of thing, and that's the rationalizing technique or method or whatever. So let's say we have a function, square root of x plus 1 minus 1 over x. And we want to see what happens, what's the limit as x approaches 0 of this function, of the square root of x plus 1 minus 1 over x. Well, in this section you should expect that when the problem starts, if you just try to put this number in, you're going to have trouble, and we can see you put a 0 in for x, and you have a 0 in the denominator. So right away you have an issue. So what we're going to try to do is alleviate that problem. So for reasons that seem really not obvious right now, what we're going to do is multiply by the conjugate of the numerator. So, and the limit of this function is going to be equal to the limit of this new function. The limits are going to be the same. We can do a lot of cool things to these functions, and their limits will be the same. So when we multiply these out, we'll get the square root of x plus 1 times the square root of x plus 1. So you get the square roots cancel each other out because they're the square root of the exact same thing. So you get x plus 1. And then you're going to get a positive square root and a negative square root. They're going to cancel each other out. And so negative 1 times 1 is negative 1. And here we're going to get x times the square root of x plus 1 plus 1. And so this will be equal to the limit, as x approaches 0, of, but let's not waste ink, virtual ink. Those cancel each other out. So we get x over x times the square root of x plus 1 plus 1. And now, here would really be the big no-no if this was an actual, if we were saying that these functions are equal, but we're just saying their limits are the same. So the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now if we put 0 in there, let's see what happens. We'll get 1 over 0 plus 1, that'll be the square root of 1. So that'd be 1. And then we're going to add that to 1. So this limit would be just 1/2. Right. And what a beautiful thing that is. Okay. I said we were going to have one more thing. This will actually be the last thing. Something called the difference quotient. Okay. And in the near future we'll know what this difference quotient is actually used for. But the difference quotient is f of x plus h minus f of x over h. It's super awesome, really cool, but you don't know the meaning of it right now. But we are going to use it, we're going to work on it. So let's just do a quick example of, let's see, f of x is x squared minus 1. And the thing we're really interested in, always we're interested with this difference quotient, is what happens as h goes closer and closer and closer to 0. What happens as h becomes really, really, really small, negligibly small. So what we're interested in is what's the limit as h goes to 0 for the difference quotient of this function. So to see what that means is, first we're going to do f of x plus h, which means x plus h is going to go into x in f of x. So x plus h gets squared, just like x gets squared, and then we subtract 1, so that's f of x plus h, minus f of x, and f of x is just x squared minus 1, over h. Okay, so the problem with this, no surprise, we get a 0 in the denominator. We can't have that happening. We can't divide by 0. So we've got to mess around with this a little bit and see if we can use maybe the canceling or the rationalizing technique to have a limit that we can actually substitute 0 into and not have a problem. So the limit as h goes to 0, let's just try and square this x plus h. So that's going to be x squared plus 2h plus h squared. And then we subtract the 1, minus x squared plus 1 over h. Okay, I'm going to have to scroll down here. So now we have the limit as h approaches 0. Okay, so now x squared minus x squared, they will cancel each other out. Those guys are gone. Negative 1 plus 1. This is going to be an all too eerie coincidence that happens every time you do one of these, or a lot of times. This is the way it'll happen. Only the things with h's in them are left. So we get h squared plus 2h over h, and so we're going to factor out an h in that expression. H times h plus 2 over h. Okay. This is what I was missing here. Hopefully you got mad earlier and said that's not right at all, because this should be 2xh. 2xh. So this should be xh. Actually, it should be no, that shouldn't be what it is. This should be 2x when we factor out an h from everything. Alright, my apologies. But now we can cancel out the h's. And now this is equal to the limit as h approaches 0 of h plus 2x. So now let's try again putting 0 in for h. What happens when we put 0 in for h? 0's gone. It's like not there anymore. And so all that we have left is 2x. Okay. So good job, you analyzed it, but the meaning of that will be revealed later on. But that does it for this intro into 11.2, and I hope it was helpful.